The secret of your success lies in the power of choice. Silicon, silicon carbide, and gallium nitride power semiconductors come with very unique characteristics, offering different benefits. To provide the highest level of system performance in your application, you have to know what each of these technologies can bring to your designs. Silicon, silicon carbide, and gallium nitride, when to use them. Gallium nitride is a technology of choice at fast-switching frequencies, providing the highest efficiency and power density at an overall optimized system cost for power-hungry applications. Wide bandgap materials complement silicon solutions, pushing the envelope of power efficiency, size, and weight reduction further for even higher levels of performance and enabling new topologies. Silicon carbide can withstand high temperatures and harsh environments. In addition, the possibility to use standard drivers with it makes silicon carbide an easy-to-use option for improved performance compared to silicon. Choosing legacy silicon provides you with the best price-performance ratio. This mature technology addresses a large variety of use cases in which price performance is desired. We know that the choice is not easy, but as your trusted partner with our several decades of experience in power semiconductors, Infineon, the expert in all three power technologies, is there to help you. We are also a committed and well-positioned supplier to fully support your growth at the highest quality standards. Our ramp-up capability, as well as 300mm wafer fab for power semiconductors and continuous R&D investments in next-generation wide bandgap and silicon technologies, together with our technology know-how, is all there for your success. Choose from our broad power portfolio of high-quality, highly efficient, and ease-of-use products. Visit our website to learn more about wide bandgap technologies.
Hello everyone, and my name is Sui, and I am from EPSC Lab in Hanoi University of Science and Technology. And I also a hardware engineer in EPSC Lab company as well. And thank you for giving me a chance to be here today to share my research on topic modeling and mitigation of common mode EMI noise for LLC Resonant DC-DC converter. Okay, so here we go. About this presentation, I have 5 parts to verify the motivation of this research, and then the model and some technique to reduce the common mode noise are proposed and verified through the simulation and experiment, and finally its conclusions. Okay, first we need to look around the development of power electronic. So I have 2 examples, one in the electric vehicle and one for the information communication technology. And for the first and for the second reference here, and about the electric vehicle, and you can see that in 2024 the development rate can up to nearly 30%. And also in the electric vehicle, there are a lot of power electronic converters, such as onboard charger, the low voltage DC-DC, and sorry. So and design for the information communication technology, and the forecast of electricity consumption can up to above 8,000 terawatt-hour, and in there more than 1/4 energy consumption is for the data center applications. So they are raising the the demand of improve the cost efficiency by either reduce the initial cost to production the power converter, and also for the running cost by increase the efficiency of the power electronic converters. And besides, we see that the large development of compact products such as gaming laptops or for the all-in-one computer. And here is an example from the studio display from the Apple. In there, we have a power electronic converter. We have the AC/DC state is the power factor correction, and DC/DC state is in this application is LC converter. And you can see that the volume is really low, and the thickness is just about 18 millimeters. So it's raising the demand of high efficiency to reduce the running costs and high power density and low profile converter with these compact applications. And for the DC/DC state and the LLC Resonant converter is a good candidate for this application. For the application require low profile and high volume and high power density, because it have the soft switching characteristic in full load range, and so the switching frequency can push up to several several hundred kilohertz to megahertz range. And for the conventional design, the efficiency is around 97%, and the power density is around 100 watt per cubic inch when it operates at 100 to 200 kilohertz according to the reference line. And to be further increase the power density to meet the requirement of all of the application, and also to reduce the running cost, and they need to be trained the design. So here is an example for the conventional front-end converter from GDK. So you can see that it is a 600 watt power supply, and the thickness is approximate to 40 millimeter. So it's really hard to meet the requirement of volume and thickness of those applications mentioned before. And so we need to change the design to like a good option to increase the power density is by using the planar transformer, planar magnetic for the conventional vertical magnetic here. So we can increase much power density. And you can see here's an example from the reference one. The power density here is up to 1.5 kilowatt per inch, cubic inch, and the thickness is just about 10 millimeter. And also when we push the switching frequency to several hundred kilohertz, we can train the wire one into the PCB winding. By using the PCB winding, you can integrate all the other components into the power converter, and also you can train the way to place the Cooper trace for the fully interleaved between primary side and secondary side winding. So we can easy to integrate the resonant inductor into the transformer to increase the power density higher. But we also have problem with this structure, and because we have the large overlapping between two adjacent layers, so there will be a capacitor, a parasitic capacitor between two layers. So and especially as I say, we need to improve the efficiency of the power converter. So we normally interleave the primary side and secondary side of the winding of the transformer. So it will build there will be a parasitic capacitor between primary side winding and the secondary side winding, and this called interwinding capacitor, and this will lead to the problem with the common mode noise, and so we need to address this problem. And for the commercial product, there's a lot of standard that used to limit the EMI noise level from the commercial product. And here is an example from the 6/22, the conducted noise from the 150 kilohertz to 30 megahertz. And so for the capacity and the noise level needs to be below the maximum, below 60 decibel microphone. So, and also from the reference tree, we can see that before and after we address the problem, address the effect of the intervening capacitance of the transformer, the noise is really like, it can be reduced up to nearly 30 decibel. So it's really important to address the problem with the parasitic capacitance. And so here is an example of the conventional front-end converter. We have a PFC state and DC-DC state. And we also have the EMI filter at the input side. But this EMI filter can take up to one third or 1/4 total volume of total power supply, and according to the reference tool. So we can reduce the power, we can increase the power density of the power supply by changing the conventional magnetic to the planar transformer. But we also have to reduce the volume of the EMI filter here to further increase the power density of the power supply. So here, this is a key factor. We also have some, for the conducted EMI noise, we have two kind of noise. We have different source of noise. This propagate in the opposite direction between two lines of power supply. And because we have a buck cap between, we normally have a buck cap between the PFC state and DC-DC state here. In this case is LLC converter, but we have a buck cap here. So the difference of noise will internally loop through the buck cap and return to the LLC converter. So it's not influence to the AC line here. So it's not influence to the difference of mode performance of the power supply. And also we have a large boost inductance in the PFC state, so it will block the difference of noise come from the DC-DC state to the AC line. But for the second scenario is the common mode noise. We have a common mode noise here. It translates in the same direction between two lines and returns through the power of the PE of the power supply, and it returns to the AC line and create the problem with the EMI filter. So in this case, in the DC-DC state, we just focus on the common mode noise to address this problem. So we have some technique to reduce the common mode noise. First, we can use this because we have large capacitance between primary side and secondary side. So we can use a shielding between two layers and to block the EMI noise. The common mode noise now can flow through from the primary winding to the shielding and back to the primary. It's not influent to it not translate to the primary side, but because we use another layer for shielding, so this will reduce the field factor of the transformer. That means we increase the DC loss of the transformer and increase the conduction loss. And also we have a more layer for the shield, so the PCB cost will be, I think it will be much higher. So the second technique is that using the balancing technique. Here we have the balancing technique, and we can we can create a source that have the same amplitude with the noise source, but it have it out phase and they are out phase with each other. So like you can, so the noise can eliminate each other and internally loop in the DC-DC converter, not flow to the AC line. But because you have to create exactly amplitude and out phase with two noise sources, so this is really sensitive to the tolerance. There's a tolerance of the particle component here. And also we can propose public propose the new structure of the converter and redesign the transformer, but they reduce when for the redesign transformer, they reduce the interleaved structure of the primary winding and the secondary winding. So the IC loss will increase due to the proximity effect. So it will increase the conduction loss and reduce the power, the efficiency, and also for the new structure, it may be difficult in modulation control, or maybe the balance to balance current between two phases of the interleaved structure. So this study, I will focus on modeling and propose some techniques to mitigate the common mode noise to reduce the sensitivity of the method, and also not influence to the transformer loss. Okay, we move to the ninth section. Oh, sorry. Some problem with my slide. Oh, here. So we move to the okay, we move to the model, the common mode model. The first to model the common mode of common mode model of the LLC converter, we have to model the transformer because we have a lot of parasitic capacitor between primary side and secondary side. So we can model it as two capacitor here, C1 and C2 here, according to the reference line, and we just guarantee the same displacement current between primary side and secondary side, and also it can be the same store energy in the parasitic capacitor between the physical model and the lab model here. And to model the LLC converter, okay, the first I trained the transformer as the lab model here, and you can see that because I have we have the buck cap in the input side and output side of the LLC converter, but for the high frequency of common mode noise, and it can be a short wire. And also we have Allison here. We have Allison here, and this represents for the impedance of the line impedance stabilization network. It used in the test setup and for the compliant test. And in this case, in the common mode, in this case, it's equal to 25 ohm. And the first to model the common mode noise, I use the substitution theory to train all the switching node, the MOSFETs and the switching node into the corresponding current sources and voltage sources. And you can see here. And also we have some parasitic capacitance between the switching node to the PE, to the chassis, and but for the commercial product, and this parasitic capacitor can be this parasitic capacitor can be eliminated by connect the heat sink of the MOSFET, primary side MOSFET to the ground of the converter. So this capacitor is shorted to the ground, so it's not influenced to the EMI trigger. So in this model, we can eliminate this capacitor, and also because the switching voltage of the half of the rectifier also have the same amplitude but alpha with each other. So the noise in here, we carefully design, we can create two capacitors here in the same capacitance. So this can be eliminate each other. So we could, and also not consider for this capacitor here. So and then I use a superposition theorem to determine what noise source and what source influence to the common mode noise. For example, for the voltage source across the low size MOSFETs of the LC converter, you can see that when we consider this voltage source, other current source will be open and other voltage source will be shorted, and you can see that for the VI, when the V prime is shorted, so the current will flow through the resonant tank and back to the VI, so it not influence, it not affect the common mode noise. and another noise is weak right. And you can see when we consider this source, the common mode noise will flow through the parasitic capacitance of the transformer and back to the PE and return through the addition here. So it affects the common mode current in the LLC converter. And I do it for the V1 and V12 here and for the EI. So we can determine the final model in this figure. And you can see that we just have V prime the parasitic capacitance of the transformer in this model. So we can easily use the Ohm law to calculate the common mode noise by calculate the voltage across the addition here. It is the voltage noise when we measure in the test. And because V prime is a square voltage, and for the duty cycle is equal to approximate to 0.5, and the amplitude equal to the DC voltage here. And in this case, maybe it's about 400 volt for the output of the PFC. So we can use the fast Fourier transform to calculate the common mode noise across addition here. And it is so in this formula. And to verify this model, I have the simulation using LP-SPI, and all of the parameters of the LLC converter are showing here. And I compare the calculation result with the physics model of the LLC converter, and you can see that the calculation result and simulation result is quite fit up to maybe 10 megahertz range. And above this frequency may be due to the non-linearity of the MOSFET model, and also the different phase time and full time of the noise source. So it have a little bit different here, but it's not effect to the EMI filter design, because when we design the EMI filter, we just focus on the cutoff frequency of low frequency here in the first or second or third harmonic order of the noise band. So it's not different. It can be used for the EMI filter design. And also for the second result, I check the influence of other parasitic capacitors like the VC, like the C1, C2, and the CPI here. So in this case, I put it equal to about 20 to 30 picofarad, and so you can see that it is not much difference for the without it, because actually the interwinding capacitance of transformer is really large, and it can be up to nanofarad range. And also, as I say, they can eliminate this capacitance by by connect the heatsink to the ground, and because the voltage here is maybe is really low, about several 10 of volts, so it's not much influence. So you can see that the common mode noise is really large. So I think we should find some technique to reduce the common mode noise. So I also have some techniques to reduce the common mode noise. But the first, and normally we to reduce the ripple voltage, ripple output voltage of the LC converter, we can put output filter here. But in this case, it's not influent to the common mode noise, because the noise will flow through the input capacitor here and back to the PE and influence to the common mode noise. So we can separate this inductor to two parts, or we can use a couple inductor here to insert a high impedance component into the main loop of the common mode noise. So the noise will be blocked here and return internally in the transformer. But in normal, because the high output current, so this inductance is about like several microhenry to several 10 of microhenry. So it's just good in high frequency range for the common mode noise reduction. So to further reduce the common mode noise, we can add a low impedance part for the common mode noise return from the secondary side to the primary side by adding the capacitor across the transformer. But actually it's work, but actually we have another problem, because we have the safety standard So for the leaky current, so maybe this capacitance will be limited. And also for some EMC tests, like lining source test, for when you like put the 4,000 volt or 5,000 volt into the input side of the converter, it may be influence to the output side of the converter. So this capacitance have to carefully design the value of this capacitor. And so because the capacitance is limited, so we can also add another high impedance component into the main loop of the common mode noise. So in this case, I choose the input side of the LLC converter because the voltage here is really large, so the current is low. So it's not influence much to the efficiency of the power converter. And we can further reduce the EMI noise. To verify all the technique, I have simulation with LD SPI, and when I separated 20 microhenry inductor into two parts, 10 microhenry inductance, and you can see that in the first when I'm just put inductor here, so there's no difference between with and without an inductor, because I say that it will loop through the input capacitor, and when I separated it, we have the same inductance, but actually the noise is reduced from maybe 5 megahertz to the 30 megahertz, and it can be reached about nearly 10 decibel microphone. But it's just a little bit, so we can further reduce the common mode noise by add the low impedance bar, add the capacitor across the transformer. In this case, you can see I add a 4.5 nanofarad capacitance, and the noise is reduced further from 1 megahertz to the high frequency range. And actually, if we not accept this this is the noise level, we can add the common mode choke just for 450 microhenry. So the noise can be reduced from the first harmonic order and can be reached more than up to 30 degree decibel microphone to the high frequency band of the common mode noise. Okay, so to verify all these simulation results, I also have the test with the experiment and test with the 400 watt LC converter, and I have a license, IC license here, and a special analyzer to display and the noise from the test from the converter, and the listen to maintain the impedance of the grid. And because I don't have DC listen, so I have to use the DC the PXC state operate with the LC converter to connect to the AC listen here. And so I have to note that this experiment is only used to demonstrate the effect of the proper techniques, not care about the absolute value of the common mode noise reduction. So with the first technique, I separated 10 microhenry inductor into two parts, and you can see that before and after I use this technique, and the noise actually reduced maybe more than 10 decibel microphone about above 10 megahertz. Here is 10 megahertz here, so it's really reduced, and the low frequency noise remain the same. And then for the capacitor across the transformer, and in this case you can see that I used 1.7 nanofarad capacitance, and the noise reduced more than 25 decibel microphone from 1 megahertz, and before and after I use the capacitance across the transformer, but at low frequency you can see it remain the same and really high, because actually this noise, because I don't use the input filter, and so the noise is only the differential mode noise from the PFC state, and so I will show it later. And finally, I use the common mode choke here, and you can see that actually it also work as well. Like it also work and reduce more than 25 decibel microphone before and after, and I have this common mode choke. And Also, has no influence to the low frequency range. I say that actually it's just a different noise from the PFC. So, so how to say? So the experiment is only used for demonstrate the effect of the techniques. I'm not considered to the absolute value. If you like, if you want to want to know exactly how much reduction of common mode noise we have to consider, we have to have a DC listen and have to consider to the parasitic parasitic component of the inductor, of the capacitor, and of the common mode shock as well. And maybe it will be the next like it's next in the future. Okay, so I have like I say that as the low frequency is only different noise from the PFC, and when I just operate the PFC state, I'm not using the LC converter. You can see that the low frequency noise is remain the same, and actually due to this loop, so it's just different noise. So that's why the noise at low frequency is not influenced by the common mode shock, because it's already different noise. And that's all much of my okay, so here is the reference. Thank you for listening. Yeah, thank you. So that's all my presentation.
Okay, let's move on the question, answer and question. So we have question from Tương PV. So please unmute and
yeah. Hello. Thank you for the presentation. I have a question regarding shielding of the transformer. So my question is, have you tried to, like in the planar transformer, you put the copper shielding like the normal transformer to see how effect to the EMI?
Actually, this like here you can see the effective of the shielding methods. You can see that the noise like it can be reduce a lot of common noise. And actually, for the ideal case, there's no common current from the primary side to the secondary side when you use this shielding method. And I would say, I think for the shielding method is really good when you need to increase the power density of the converter, because you don't have to use any passive component and you just like increase the technique of the PCB to add another shielding layer. And yeah, and you want to ask the way it's operated, right? Or something.
It's like you know, in the conventional transformer to shielding, we put an copper wire or how to say called barely copper around the transformer to wrap up and shield. So have you tried, like, can you back to the power supply from TDK in the some presenting? Yeah.
Oh, yeah.
Yeah. So you see they have like seal outside, right?
No, actually it's just like
No.
okay, outside. Actually, I think okay, I understand your question. I think for the shooting outside, it's just to like how to say to block the noise from the air gap of the transformer, to coupling to add the ground component from the air gap transformer for the like the magnetic coupling around to the around component. But in this case, you can see here, in this case we have the shielding between secondary and primary side to block the noise from the primary to the secondary side. It just flows from primary to shielding and back to the primary. It's not like yeah, it's not influent. It's not like the shield around the air gap of the transformer.
So no effect, right?
Yeah, it's not effect.
Okay, thank you.
Thank you for the question.
okay, there's a question. There's a question from Kisman. Based on slide number 6, is there Thus, let the less power converter proportional to the volume
Yeah.
of
Yeah.
the EMI filter.
Sorry, I can hear you.
His question is the larger rated power of the power converter proportional to the volume of the EMI filter?
Proposed. Actually, here, yeah, it's not for the proposal technique here, right? How to say? Actually, it's not much influence to the how to say to reduce the input filter, but when for the EMI filter at the input side, you have to like clean all how to say clean all the propagation part of the EMI noise to like to increase the effective of the EMI filter. And but when we know the noise source from the DC-DC converter, we can address problem right in the right in the I say right in the right in the noise source in this case right in the transformer and in the input side of the LLC converter. But when you not address the problem from LLC converter, you have to like increase the state of the EMI filter. You have to increase the inductance of carbon molecule, increase the how to say the capacitance. Actually, like it have another problem with parasitic component, and maybe when we use in my case, I think that when we address the problem of common mode noise right in the noise source, it will be better in like total volume of the EMI filter and some technique I propose. If you just use only EMI filter, like it will be much problem. We will have to increase the state and EMI filter, increase the value. But actually, when you increase the value, maybe it's like due to the parasitic component, it will be like degrade the EMI filter performance. So I think when you address the problem right in the EMI source, it will be better.
Okay, Kisman, is that answer solve the question?
Yeah, it's my answer. So if you like to further improve you want to further improve the power density of the converter, maybe I think you should use the shielding technique, because you don't have to use any like any other component.
Okay, so we can move on to another question. Dr. Thang, please envoy and give the question.
Yes, my question related to the sealing technique. Do you have any reference who working on this sealing technique? Because of my concern is maybe they can generate some eddy current on that sealing, right? Because that sealing is not this material, and that is material is maybe the copper.
Yeah.
And then maybe that can generate some loss on that sealing. And second one is I don't know whether this sealing will connect to this thing or that floating. If that is floating, that may cause the other problem of the radiated noise.
Yeah, thank you for your question. And let me move to the slide. Oh, any problem? Here. Okay, so for the first question about the eddy current, actually some public from CPAS and other lab, I see that they can change the technique of the shielding layer is like below 0.5 OZ. So it actually is not much influence to the about the 1 kilowatt LLC converter. There is a total efficiency is reduced about 0.1 to 0.2 percent. And also they are also propose some technique to increase. They can increase the total efficiency of the LLC converter by using this shielding layer to the primary side winding. That they use a half of the primary of the shielding as a how to say as a part of the primary side winding, and then the current on the primary side will reduce, so they can increase the total efficiency of the LC converter, and it's not influence to the EMI noise because they guarantee that the gradient voltage of the shielding is the same with the same with the secondary side winding, so they can reduce the common mode noise, and also they can improve the efficiency of the converter. So actually, they can improve the efficiency when they using the shielding technique to block the common mode noise. Yep. And for the second question is that the connect terminal of the shielding. Actually, the shielding can connect in the ground of the primary side or the ground of the secondary side. We just have to guarantee that the gradient voltage, if we connect to the primary side, the gradient voltage of the secondary of the shielding and the secondary side have to the same, to not have a displacement current from the shielding to the secondary side. That creates the common mode noise. Or when we connect the shielding to the secondary side ground, so the gradient voltage of the shielding has to the same with the primary side winding. So there's no current from the primary side to the shielding, and so there's no common mode noise. And if we float the EMI shielding, we float the shielding, so the current from the primary side to the shielding, and the shielding will the current from shielding and flow through to the secondary. So it will like reduce the effective of the shielding method, and maybe it has some resonance problem and increase the noise from some frequency in total band of the common mode noise. Yeah, and also I have some reference here, shielding method from CPS in 2023 and 2020. Yeah, a lot of shielding method here. And almost from CPS, and because they want to improve the power density, so they can use shielding method because they don't have to use other component.
All right, thank you. Yeah, thank you for your answer.
Thank you.
We have one more question from Tiep. Tiep, can you directly ask the question?
Okay, thank you so much. And I want to ask about the model, the simplified model.
Here.
Okay, here. As assumption. No, this line here. Okay. As you said about the assumption, when the CN1, C1N, and C2N is equal, and the excitation is V1N and V2N is equal, but amplitude, but 180 phased out of phase. So the effect of the C1N and C2N is not contribute to the CM noise. So what is problem when the C1N and C2N is mismatched?
Yeah. Okay. So when so the capacitance C1 and C2 can be mismatched, or the phase or amplitude different from the V1, 2 and the V2N here, and actually it's not much influence effect to the total common mode noise, because I say that for the conventional power supply design, or maybe now maybe like 48 voltage at the output side, or maybe 12 voltage at the output side. So the dB particular here is sorry. And then actually it just not contribute much to the total common mode noise level, because it's just like several 10 of picofarad, and the dB positive voltage is very small. So okay. So do you
Yeah. As you mean that the C1n and C2n is not contribute much to the CMOS?
Yeah, it's not contribute much because it's have just a little bit difference in capacitance, and also the dV validity is low compared to here. Here is 400 volt, and here it's just like how to say more than 100 volt, or maybe several 10 volt here, and also the parasitic capacitance just several 10 of pico, and here can be up to nanofarad range.
Okay. So I have a curious about when as you said about this topology here is bulk. So when the topology is high step boost.
High step boost.
This means the dVd of the C1n is very high.
Okay. The output side is larger than the input side.
Yep.
Yeah. How to say? I don't know, but actually in this application, the input side is 400 volt. So if you push like, maybe I think in your application, the voltage at the input side will be much lower, right? So actually, in this case, if you want to care about the influence of the two this capacitor, we can like also because the
this means when in application that that the input is smaller than the output, so the C1n and C2n is highly carefully.
Actually, I'm not having any experience on this, but actually
Okay.
in my case,
Okay.
and I think that it's just like a little bit different in capacitance. It's not much when you carefully design it. So it also not much contribute to the total EMI not in the converter.
Okay, thank you so much. Thank you so much. I don't have a question.
Oh, there's the time, so I have one more question. Like, how do you model the converter for the switch, and how use equivalent with voltage or current source? How you determine that?
Actually, like the current here. Okay, we just use we not use any like any the waveform or the amplitude of the current source. It have to the same waveform with the current the original MOSFET or the switching node. But actually, we just know that because, and I say finally we just have a voltage source influence to the common noise. So we not care about other waveform of the voltage and the current, but for the V prime here, and actually because the LLC resonant converter is operating near the resonant frequency, so the voltage drop on the resonant time is smaller compared to V prime here. So we can approximate the V prime equal to the switching node on the half rate of the LLC converter. So it's just a square voltage with a duty cycle equal to 0.5. Yeah. So we not consider to add the voltage source into resources.
Okay, thank you for the answer.